Hello everyone, this is Anil Singh and welcome to Medical Imaging Physics, the Essential Lecture 1, an introduction to the physics concepts and underlying principles of medical imaging. Okay, so for Lecture 1, these are our learning objectives and goals. 1. Build a foundation by learning the basics of atomic physics and its application to diagnostic medical imaging. 2. We should be able to describe the electromagnetic spectrum with a focus on the ionizing portion of the spectrum. 3. Learn the mechanisms by which ionizing and particulate radiation interact with matter. 4th, learn the processes of radiation attenuation when it traverses through matter. Okay, so in medical imaging of the human body, it always requires some form of energy which has the ability to penetrate the human tissues and the remnant energy be captured by a type of detector, whether this is analog or digital. Analog being referred to as the old screen and film, whereas digital detectors have become a more modern replacement. So in diagnostic radiology, medical imaging utilizes electromagnetic radiation to perform such diagnostic studies. These can either be categorized as either ionizing or non-ionizing energies. For example, non-ionizing radiation modalities would include MRI and ultrasound. Ionizing radiation, on the other hand, would be X-rays, computed tomography, mammography, and fluoroscopy. Now, one thing that we should always note that in diagnostic medical imaging, a compromise must always be made between the patient's quality of the image and the exposure of electromagnetic radiation to the patient. For example, higher resolution X-ray images are made with the use of higher radiation doses, or better ultrasound images come with the use of using larger power levels, and better MRI images are made with longer scanning times. However, it is never acceptable to deliver excessive exposures to the patient at the expense of acquiring the perfect image. There must always be a balance between patient safety and image quality. When we talk about electromagnetic radiation, or EM radiation, we are describing a method by which energy is transferred via EM waves. There are two correct ways of describing EM radiation: a classical approach, which describes it as waves, or the quantum approach, which describes it as quanta packets of energy called photons. Electromagnetic radiation are essentially massless packets of energy which have no associated charge, travels at the speed of light in a vacuum, and exhibit both particle and wave-like characteristics. The EM radiation spectrum comprises of a large array of different wavelengths. Now, the big difference between the spectrum is that it can be divided between the non-ionizing radiation side and ionizing radiation segment. Let us now differentiate between the term ionizing radiation and non-ionizing radiation. So simply put, ionizing radiation is that radiation that contains sufficient energy so that when interacting with matter can cause changes in the atomic structure by the removal of one or more orbital electrons. On the other hand, non-ionizing radiation does not have sufficient energy to modify the atomic structure. However, it can briefly excite the atom, but eventually it will return to its original state. Okay, so now let's briefly talk about the structure of the atom. So as we know, the atom consists of a nucleus, which contains both protons and neutrons. Orbiting around the nucleus are the electron orbits. They're described by the shells labeled K, L, M, N, and O. Now, if we consider why the nucleus does not explode apart because of the similar charges of the protons, this is because there's a force called the strong nuclear force, and this in essence binds together the nucleus and counteracts the net repulsion force that is imposed by the adjacent protons of the same charge. As previously mentioned, the orbital shells are named in the order K, L, M, where K is the innermost shell. Each shell can hold a maximum number of electrons demonstrated by the following equation. Number of electrons equals 2n squared, where n refers to the orbital shell, where k equals 1, L 2, and M 3. For example, if we want to figure out how many electrons can be held in shell M, then using the equation above, we see that 2n, where M is the third shell, therefore it is 2, 3 squared and we get 18 electrons being the maximum number of electrons that can orbit in shell M. Another nuclear force that we should discuss is one called the orbital binding energy. This is the energy that is required to remove an electron from an orbital shell. Take, for example, the first diagram to the left. This schematic shows the hydrogen atom, which has an atomic number of 1, and here we can see the K shell, L, M, and N shells. Here we can see the energy required to remove the electron from the K shell is 13.5 electron volts. And what we notice is that as we go further away to the outer shells, for example L, M, or N, we see that the binding energy, or rather the energy required to remove the electron from these shells, decreases. This is because it is at a further proximity to the nucleus of the atom. Therefore, the energy required to liberate these electrons are therefore less than the shells closer to the nucleus. Here to the right, we see the same concept but applied to the tungsten atom. Unlike the hydrogen atom, it requires a considerable larger amounts of energy to liberate or ionize these atoms, as we see by the values here. So what happens in an example where an orbital electron is liberated from an inner shell, for example, the K shell, as we see in the diagram here? Whenever an electron is removed from a shell, it is called or produces a vacancy. When a vacancy is formed, it is almost always filled by an outer shelled electron through a process called an electron transition. So this is whereby an outer shell electron jumps from its position to fill the vacancy in the inner shell. So what happens in this process is that whenever there's a transition from an outer shell to an inner shell, there's going to be a release of energy which is proportional to the difference between the two binding energies of those shells. So as it transitions, it releases energy in the form of an X-ray. And the energy of this X-ray equals the value or the difference between those two orbital shells. So when we talk about electron transitions, it is not always that when an outer shell electron transitions to an inner K shell, an X-ray is formed. So for very low Z elements, there is actually a competing emission called an Auger emission. And this, instead of releasing a characteristic X-ray, the energy is then transferred back to the outer shell orbital electron, which is then ejected from its orbit. Now once again, in comparison, this only occurs for mostly low Z elements. Okay, so now we're going to talk about ionizing radiation and its interactions with matter. Now on this slide, we're going to first discuss about particulate radiation as it interacts with matter as opposed to X-ray and gamma ray photons, which we'll get to shortly. So first, when we talk about particulate radiation, we're referring to, once again, electrons, neutrons, or protons. Now, in diagnostic radiology, we are essentially only concerned with the electron. Okay, so now when electrons or particulate radiation interacts with matter, there are three possible types of interactions. 1, excitation. 2, ionization. And 3, radiative losses. So we'll discuss them briefly, one at a time, of course starting with number 1, which is excitation. So in this scenario, this is the transfer of some of the incident particle kinetic energy, once again we're referring to the electron, to an orbital electron of the atom itself. And what this does, it briefly allows the electron to move to a higher state, but at the same time does not possess sufficient kinetic energy to actually liberate it or eject it from its orbital shell. Now this is a temporary effect because shortly afterwards the electron that its energy was given to returns to its lower state. On the other hand, when we talk about 2, ionization, the incident particle or the electron has sufficient kinetic energy to actually cause the removal of the orbital electron from the atom of which it's interaction with. So this means that the incident electron has sufficient kinetic energy, or that it is greater than the actual binding energy of the orbital shell electron. And as a result, it is actually ejected from its orbital shell and causes an ionization event. 3. Radiative losses. So in this scenario, results because of the attraction of the negatively charged electron and the positively charged nucleus. So if you consider an electron that's traversing close to the atom, because of the likely charges, which is the negative once again and the positive nucleus, as the electron traverses close to the nucleus, it undergoes or experiences, of course, an attraction force. And as a result, the kinetic energy is lost because of its attraction to the nucleus. And because of this change in its trajectory, it actually loses some of this kinetic energy. And in this deflection, the energy that's lost is converted into an X-ray photon. Now we're going to talk about X and gamma ray interactions with matter. Now there's quite a few more concepts to discuss when we talk about X-ray and gamma rays interactions as opposed to particulate radiation. So firstly, let's first get accustomed to the 4 different types of interactions that can occur. There is 1, photoelectric absorption, 2, Rayleigh scattering, 3, Compton scattering, and 4, peer production. So the next couple of slides we're kind of going to discuss each one in detail and the probability and differences between each one. Okay, so the first one we're going to talk about is Rayleigh scattering. And as you can see from the diagram, it's always good to describe these interactions when starting with the statement, an incident photon. Okay, so we have an incident photon which goes on to interact with an atomic structure. So here we can see the nucleus and the orbital shells. And what happens in a Rayleigh scattering is that, well, the incident photon typically does not have enough energy to cause ionization. So what happens in this scenario is that the incident photon goes on, interacts with the atom as a whole, and then is scattered at some different direction than its original path. Now, in Rayleigh scattering, this only occurs at low photon energies, and this is typically between 15 and 30 keV. Now, one thing to note as we were talking about diagnostic radiology on a whole is that this interaction typically occurs within the energy range found in mammography imaging. Okay, so we're going to talk a little bit more, or quite a bit more about mammography much later in this course. But just note for now is that in Rayleigh scattering, that is the most common type of interaction in mammography imaging. So let's read through the points once again. So when the incident photon excites the atom, a photon of the same wavelength and energy is emitted but at a slightly different angle. Okay, so what is the consequence of this interaction in general? So if we have an incident photon that is scattered at some random direction, then of course this may cause the X-ray being produced, or the film or the receptor capturing the X-ray, essentially to have a deterioration in the image quality, because of course this is coming from an unknown direction and therefore carrying incorrect information towards the X-ray film. Now this accounts for 5% of X-ray interactions above 70 keV and approximately 10% at lower energies lower than 30 keV. The next type of interaction that we will discuss is Compton scatter. And Compton scatter is the predominant interaction in the diagnostic X-ray range. So in this interaction, what occurs is that when an incident photon has sufficient energy to liberate an outer shell electron, once again, this means that the incident photon has energy greater than the binding energy of the orbital shells. Whether this may be the K shell, L, M, N, it is greater than those shells' binding energy. Once again, because the incident photon's energy is greater than the binding energy of the shells, the likelihood of ionization is high. So in this scenario, an incident photon goes on to interact with the outer shell electron, and once again, because its energy is greater than the binding energy holding the electron in that shell, that orbit, is actually knocked out of it and creates a vacancy in that shell. Now the difference in the binding energy and the energy of the incident photon results in the scattered photon at some angle. So let me just get the pointer here. So here we have the incident photon, and it goes on to interact with the atom as we see here. And in this scenario, the incident photon, its energy, is greater than the binding energy of this outer shell. And as a result, it actually causes an ionization event. meaning that there's a removal of the electron from its shell. So this is called a recoil electron because it is knocked out of the shell by this incident photon. Now the difference in the energy of this incident photon and the orbital binary energy of the shell results in a scattered photon at some scattered angle. Okay, so just something to note, the scattered photon, if it has sufficient energy, can go on to cause further interactions later on. So let's now talk about the actual scattering event as a result of Compton scatter. So the angle of scatter for both the photon and the electron depends upon the incident photon energy. Okay, so as we just discussed in the previous slide, as the incident photon goes on and strikes an orbital electron, because its energy is greater than that of the orbital binary energy, it is actually knocked out of its orbital shell, and of course it is scattered and now termed a recoil electron. The difference between the incident photon and the orbital binary energy of that electron, it results in a scattered photon at some scattered angle. Now let's talk about the range of those scattered angles. Firstly, referring to the recoil electron, it is important to note that the maximum angle of scatter for this electron is 90 degrees. As opposed to the scattered photon, it can have any angle included in 0 up to 180 degrees. And of course, 180 degrees means that it can be backscattered, which is the opposite direction than the incident photon. So in diagnostic radiology, majority of the energy is transferred to the scattered photon and not the recoil electron. So the larger the photon energy, the angle of scatter of the photon decreases. So if we take a look at the diagram to the right, we have 3 different energy ranges. We have 140, 80, 20 kilo electron volt. So here, what is this diagram telling us? Let's first talk about the lowest energy curve. So here we can see the incident photon is 20 keV, so this is the lowest one of the 3. And we can see when we compare it to the higher energies, we can see first of all the probability of the scatter angle is has a wide range. We can see it's anywhere between 0 and 180. So the y-axis is the probability of a scatter, and you can see that the probability of a scatter for these angles between 30 and 150 is quite high. Now, as we talk about now the 80 and 140 keV, we see that as we go higher incident photon, we can see that the probability of the scatter angle is getting closer to 0. So let's jump and take a look at the 140 keV curve. Right, so we can see that it peaks more in the range of 30 to 60. So that ties back into the point here that the larger the photon energy, the angle of scatter of the photon decreases. So referring to the larger photon energy refers to the incident photon. So as this incident photon energy is greater, the likelihood of the scattered photon being in more of a far direction increases. Alright, the next interaction that we'll talk about is now the photoelectric absorption. So unlike Compton scatter, when the incident photon interacts with the atom, or rather the electron in an orbital shell, it gives up all of its energy in that interaction. As a result, once again, if its energy is sufficient, it will cause an ionization. Once again, it's the ejection of that electron from its shell. Okay, so this is termed a photoelectron, and of course, when an electron is ejected from its shell, it creates a vacancy. So here we can see in the diagram, as the incident photon goes on to strike an electron in the K shell, it gives up all of its energy and results in the liberation of this electron. So as we discussed earlier, when an electron is removed from a shell, it is an ionization event, and now there's a vacancy in the K shell. So what happens when there's a vacancy in the K shell? As discussed in the previous slide, there's something called an electron transition, and this is when an outer shell electron jumps or transitions from its outer shell and to fill an inner shell. So here we can see an electron from the L shell jumps to fill the vacancy in the K shell, and of course the vacancy in the L shell as a result of that is then filled by an outer shell M shell electron. So what happens here is that we have two electron transitions, once again from the L to the K shell, and then from the M shell to the L shell. And whenever there's an electron transition, there's an emission of X-ray photons. So these are called characteristic X-rays. And the energy associated with these characteristic X-rays comes from the fact that there are a difference between the binary energy of the shells that wish to transverse in from. The last and final X-ray with interaction with matter that we will discuss is called pair production. Now, the first thing to note about pair production is that there's a threshold for which this interaction can take place. This is that the incident X-ray energy must be equal to or exceeding 1020 kilo electron volts, or 1.02 mega electron volts. The other thing is that unlike the previous interactions such as Compton and photoelectric, where those interactions interact with the orbital electron, in pair production, the incident photon interacts directly with the nucleus of the atom, and not the orbital electrons. So in this process, the energy is given up completely in the interaction with the nucleus, and is transformed into what we say an electron-positron pair. When this electron and positron pair is created, they can go on to cause further excitation and other ionization events within the material that which is interacting with. But what happens is that when the positron comes to a rest, it eventually combines with the electron and becomes an annihilation event. So when this occurs, what happens is that two photons are created, and they're created 180 degrees apart from each other, and they always have an energy of 0.511 mega electron volts. Let's now discuss the attenuation of X-rays and gamma rays with matter. So, X and gamma rays can undergo the following three processes when traversing through matter. This is absorption. This is where the photon is absorbed by the material itself and stems from, for example, a photoelectric interaction. 2. It can be scattered, resulting in the change of trajectory of the photon, and this stems from the Compton scatter effect. And 3. Transmission. This is where the photon does not exhibit any of the above scenarios, but has traversed through the material without any form of interaction. Now, attenuation is said to be a product of which of the following two interactions? Attenuation is a product of either, or both, absorption or scatter, and is essentially a change in the initial flux of an X-ray beam as it traverses through matter. Attenuation is a reduction of the intensity of the X-ray beam as it traverses through matter. As previously noted, this is a product of both absorption and scattering of the photons, and is affected by the beam's energy and atomic number of the material. Note, at lower photon energies, the photoelectric absorption is more likely to occur, and therefore absorption likely dominates over scattering events. On the other hand, at higher photon energies, Compton scattering dominates, resulting in a scattered photons. So previously we were more engaged with the interactions with matter. However, it is necessary to consider the macroscopic behavior of photons as it traverses a material. So for this purpose, we will introduce two new concepts. This is the term linear and mass attenuation coefficients. So while we know a primary photon may undergo more than one interaction, the linear and mass attenuation coefficient only accounts for the initial primary photon interaction. This is better modeled using complex algorithms such as Monte Carlo, and it gives a better understanding by which how photons undergo interactions. We will first talk about the linear attenuation coefficients of photons. Now note, the linear attenuation coefficient refers to the fraction of photons removed from a monoenergetic beam of X-rays per unit thickness, typically denoted in centimeters. The definition of a linear attenuation coefficient is the number of photons either removed, as previously discussed, either through scattering events or absorption events, from a beam or X-ray beam as it traverses through a segment of thickness, typically denoted as delta x. This can be expressed as n is equal to mu capital N naught delta x, where lowercase n denotes the number of photons removed, and capital N denotes the incident number of photons that comprises of that beam. Let us now use a very simple example of using the formula below. So take an example 1, a 100 kiloelectron volt photon beam traverses soft tissue where the linear attenuation coefficient of the tissue is 0.0161 millimeters. Now, if the original beam comprised of 1000 monoenergetic photons and they're traversing upon 1 millimeter thickness, then 16 will be removed either by absorption or scattering. We get to this value by using the equation on the previous slide. Lowercase n is equal to mu capital N naught delta x. So if we plug our values into this equation, we're going to get lowercase n is equal to the linear attenuation coefficient 0.016 multiplied by capital N naught, which is the incident number of photons in the beam, which is 1000, multiplied by the thickness of the material that the beam is traversing. In this case is 1 millimeter. And simply we get 16 photons are attenuated. And just remember, attenuation refers to the number of photons being removed from the beam, either through absorption or scattering events. Let us now consider a small variation to that previous example, using a larger thickness. It is important to note that the relationship of attenuation using the equation before is not one of a linear form. It is wrong to assume that for 6 centimeters of tissue, that 960 photons will be removed out of 1000 photons comprising the beam. We know that this is not true because we know typically X-rays are used to take images of parts of the body that is of course greater than 6 centimeters. But yet we get development on the film. Now if this were true, then majority of the photons will be removed and only 40 will be left to produce the film. So to accurately calculate the number of photons removed from the beam using the equation above, it will be best to use multiple separate calculations for small increments of the thickness. The smallest thickness used in the calculation will therefore be more accurate to estimate the amount of photons being removed. However, this will be a very tedious calculation. Therefore, for a monoenergetic beam of photons that is incident upon either a thick or thin slab of a material, an exponential relationship more accurately describes using the equation below. N is equal to N naught e to the power of mu x, where of course capital N naught refers to the amount of photons that originally comprised the beam, to the exponential minus the linear attenuation coefficient of material, and x referring to the thickness of which the material traverses entirely. Knowing this, let's reattempt the previous question for a thickness of 6 centimeters. N is equal to N naught e to the minus mu x, where once again N naught is the original number of photons comprising the beam, mu is the linear attenuation coefficient, and x is the total thickness being traversed. So plugging in the values into this equation, we get N is equal to 1000 e to the minus 0.016 by 60 millimeters, and we get a more reasonable answer of 380 photons being transmitted, or therefore 620 photons are being attenuated. One thing to note is that the linear attenuation coefficient speaks to the number of photons being removed through the absorption and scatter per unit thickness. Therefore, the linear attenuation coefficient mu is the sum of the potential contributions from every type of interactions. These are the ones previously discussed in the earlier slides. This will be the contribution from Rayleigh scattering, the photoelectric absorption, Compton scatter, and of course pure production. So one thing to note regarding attenuation of photons as it relates to the object density, we say that for a given thickness of a material, the probability of the interaction depends on the number of atoms encountered per unit distance of the material. Thus, material density, ρ, affects this relationship. In essence, should the object density double, then the photons encountered by the material will be twice as many for the same distance traveled. Thus, the linear attenuation coefficient is proportional to the material density. Take, for example, water and its three forms of matter, ice and vapor. Note that the linear attenuation coefficient in the state of water is greater than that of ice and then that of water vapor. On the previous slides, we spoke about the linear attenuation coefficients, which spoke to the amount of photons being removed per unit distance. On this hand, we're now going to be talking about the mass attenuation coefficient. So, for a given material of thickness, the probability of interaction is proportional to the number of atoms per unit volume. To get to the mass attenuation coefficient, we normalize the linear attenuation coefficient to density of the material. Now, let us introduce a new concept called the half-value layer, HVL. The half-value layer is defined as the thickness of a material required to attenuate a beam's intensity to half of its initial value. The HVL of a beam is an indirect measure of a photon's energy, referred to as quality. When measured under the conditions of narrow beam geometry, this refers to an experimental configuration that is designed to exclude scattered photons from being measured by the detector itself. Naturally, as photons become more penetrating, the required thickness of the attenuator will have to increase to reduce the intensity by half. Here we can see in the table to the right, increasing thicknesses for increasing photon energies. This slide demonstrates the practical experiment of measuring the HVL in diagnostic radiology for any X-ray tube. This is commonly done using millimeter sheets of aluminum as shown in the diagram to the right. Typically, an X-ray exposure is made and the intensity is measured by the radiation detector shown to the right. Sheets of aluminum will then be placed into the field and exposures will be repeated. Additional sheets of aluminum will keep on being placed into the field until the original intensity is reduced by approximately 1/2. Therefore, the total thickness of aluminum sheets placed into the beam to reduce the detector's measurement by half will therefore be the HVL in sheets of aluminum. The next concept is called beam hardening. The removal of lower energy photons from a polyenergetic beam will increase the effective energy of the beam. For a polyenergetic beam, the lower energy photons will be absorbed by the target material itself. So what does this mean in a clinical setting? This means that lower energy photons will not be able to penetrate the entire thickness of the patient, but rather be absorbed by the patient themselves without benefiting and increasing the image quality. In X-ray tubes, most of the lower energy photons of the spectrums are removed by a thin filter plate of either aluminum or copper. This added filtration creates a hardened beam with an increased penetrability and thus increased effective energy. This diagram describes or shows the effects of beam hardening as a polyenergetic beam traverses through 4 sheets of an attenuator. Here you can see, starting from the left, the polyenergetic X-ray beam comprising of different photon energies, depicted by longer wavelengths and shorter wavelengths. As the beam passes through the first attenuated material, you can see that, because of attenuation, one of the lower energy X-rays is being attenuated, thus leaving behind the resultant rays. As they pass through the second, beam hardening continues and another lower energy photon is removed, and this process is removed, keeping or leaving behind only the shorter, more energetic photons in the path, thus resulting in a hardening beam. This now ends Lecture 1. To summarize what was covered, we first spoke about electromagnetic radiation versus particulate radiation. So to differentiate quickly, electromagnetic radiation can be described as energy being transferred via waves or as packets of energy called photons. Whereas particulate radiation are those subatomic particles such as protons or electrons, and those typically have a mass associated with it. We then covered ionizing versus non-ionizing radiation. To differentiate the two, ionizing radiation has sufficient energy to cause the removal of an orbital shell electron, whereas non-ionizing radiation lacks energy to do so, but at the same time has energy to cause excitation of the atom as a whole unit itself. Next, we spoke about particulate radiation and its interaction types with matter. That would be excitation, ionization, and brimstone radiation. We then spoke about X-rays and gamma rays interaction with matter, and there we spoke about Rayleigh scattering, photoelectric absorption, Compton scattering, and pair production. We then spoke about X-ray and gamma ray attenuation. What does attenuation mean? And then we spoke about linear and mass attenuation coefficients. We then moved on to half-value layer. This is the amount of thickness of a material required to reduce an X-ray beam's intensity to half of its original value. And then we spoke about the concept of beam hardening. Now, with these 8 points, we should now be able to dive into the actual radiological imaging modalities and have a better appreciation of the physics behind each modality. The next lecture, Lecture 2, we will begin discussing the X-ray tube and the components which comprise the X-ray tube.